Welcome back, students. So, extending our understanding from the exponential growth and decay, we are going to extend our understanding to another new concept, but very related, is half-life. So, before I get to half-life, let's just look at a problem. Let's look at a problem and refresh our memory in terms of exponential growth. So, remember, everyone, P equals to P naught e to the power kt is the exponential model or decay depends on the value of k. So if your k is positive, it's exponential growth. If k is negative, it's exponential decay. Let's do the first problem. So given p equals to p naught e to the power kt and p naught equals to 500 if p equals to 680 when t equals to 5. So this is crucial. P equals to 680 and t is equals to 5. See, with this initial information, you can easily find out k, and then you can use your k for the modeling for the rest of the questions. So what do we have? We have 680 equal p naught equals to 500 e to the power kt. K is 5. So if you recall correctly, 680 divided by 500 equals to e to the power 5k. This is simply 5k equals to ln 680 over 500, and you can easily get that number in the calculator and divide by 5. There you go, you have your k. K is simply ln 680 divided by 500 divided by 5. That's your k. Now once you got your k, your modeling is like you're done. The next is just subbing in numbers. For example, what I meant by that is P of t is equals to 500 and whatever your k was, and then you have your t. So the next thing you know is, given some time, you can easily find out your population just by plugging in numbers. For example, when t equals to 10, find out the population. So it's p of 10, and you got 500 e to the power your k value multiplied with 10. You put them into the calculator, that gives you the population in 10 years. So now we want to understand something else entirely different, but very closely related. In other words, the concept is the same, but it's somehow related to another formula which we are going to discuss in a short time. So this one is related to half-life. So you need to understand the what does it mean by half-life. It's also sometimes written as T 1 over 2, T half, also written as T half life. What is this? So let me show this in a graphical manner. So if we have something, let's say here, which is that's a certain population P. So what we mean by half-life is how long does it take for that P to become P over 2. In other words, the exact time it takes. So whatever time it took, we don't know how much, but whatever it took to become half, that's half-life. And then P over 2, if you take it another half of that, so it's going to be P over 4, and we are saying this is going to take exactly the same amount of time. That's the concept. So the amount of time it takes for something to become half, that's half-life. So it can come in terms of bacteria, it can come in terms of some certain animals that are going to be extinct, or cats in a society or in a suburb, whatever the case may be, or in a radioactive material, the way the atoms decay. This formula is also given by n t n naught half t over t half. So that's the half-life, and this is the time it takes, and this is whatever the case, number of atoms, number of cats, number of human beings, number of whatever, number of birds that are going to be extinct, and this is that same number at a particular time. So given uh, one or the other, given enough information, you can always find out what would be the half-life of a particular substance. And there is an example of it, written example, like salt example here for you. If you want, you can go through it yourself first without looking at the solution, and then see if you can do it. If you cannot do it, just have a look at the solution and then try again. So that's it for this video. So this was related to half-life, a bit of extension of exponential growth and decay that we have learned in the last video. And I'll see you in the next video. Thank you.